Okay, welcome everybody to the DCSC lunch colloquium. Today our guest is Max Mendel. He's actually a member of DCSC, and he has already given a nice overview here of his career. Actually, he started with his studies in Delft. At that time, it was still called not the university, but a hogeschool. So the current term is University of Applied Sciences.
Yeah, serious.
Then he moved to MIT, where he did his PhD. Then he went to University of California in Berkeley as an assistant professor. And after that, he moved to the financial world. The WS stands for Wall Street. And then after a while, he returned back to TU Delft, where he's currently working at DCSC on the topic of economic engineering. And that actually will be the topic that he will tell us about. So Max, the floor is yours.
Thank you, Bart, and thank you for explaining this little diagram. I do want to point out to you that this is a projector space, right? So this is, I didn't come back to where I started. This is the point at infinity. That's why those two circles overlap in this way. And now that I look at it, the only thing that went wrong is that this point here projects out to minus infinity. So that means I'm going backward. But sometimes that's the feeling. Economic engineering, theory and practice. That's the title for my talk. And economic and engineering are two words that really don't go together very well. Most engineers have no idea what economists talk about, even if they try, and vice versa. Economists, even if they try, they have no understanding of what's going on. I've tried, it doesn't work. Right? Now, one thing I'd like to emphasize is that the noun here is engineering. So the way I look at economics is, from an engineering perspective. So if you're an economist, you won't understand what I'm talking about. You probably won't be interested. You probably will get angry because I'm saying stuff that you just think that this is not. So this is really geared to engineers. It was something that came out of my background in controls. And then I made a big switch to Wall Street. I was standing on the floor there and trading. I got a lot of practical experience in how to do that. And there was still a sort of, maybe that's the problem with when you get older, you feel that your life is not hanging together. There's not one story. So there was a tendency, I had the desire to put it all together. So I took this approach to all the experience I had and how you think about it, how I can view that, model that, look at from the perspective of everything I've learned in my classes and controls and the teaching I've done and all of this. So here, I started with this at DCSC. It changes every year how long it's been, but I think it's about 5 years ago now. And I'm actually quite happy and embarrassed at the same time, happy to be able to share with you. I feel we're in a nice place and a little bit embarrassed because I've really done so little. All right, but maybe that's a feeling you all academia. So with that little writer, I'm going to stop talking about me and I'm going to talk about economic engineering. Now, if there's one way in which I can summarize this business, it's that the law of demand is analogous to the law of Newton, law of motion, and the rest is details. Okay, so, but there are, this is academia, there's going to be a lot of details, and details is our profession, and that's where we find the devil and the Lord, the good Lord and everything. But this is the starting point, and at once, this is where my approach varies from everybody else's. Okay, so most approaches who try to do this, what they do is they think of price. So in economics, there's really only two things that are important. If you look at the economics of that, there's the quantity demanded. That could be apples or barrels of oil or maybe money, right? The quantity demanded is not an amount, but it is a flow, right? So many apples a day, so many barrels a day, and that's your consumption or the supply. So it's a flow variable. So it will be comparable to something we call a velocity or maybe an electric current, right? It's in items per something. Now, an economist may look at this and say, well, how do I model that? Well, associated with every flow is a price. And that's not a market price. That's a price that I am willing to pay, or I'm willing to pay for it to get it, or a price I'm willing to receive, as money compensation for supplying it. All right. So you should see the price there on the vertical axis, the flow. They call it a quantity demanded. It really is a flow demanded on the horizontal axis. And what they draw these lines. They call demand or supply schedules. The supply schedule goes up. So as you need to deliver more, the price goes up. And the demand schedule goes down because as you consume more and more apples, you're going to say, well, you're going to get sick of it. You're going to try to pay less for it. All right. And then they figure out that in equilibrium is somewhere where they cross, and then they go from there. Okay. Now, how do we set this in an engineering framework? Now, I've labeled these axes already, P and V, and it's a line. So let's call it the proportionality, the slope, the mass. So it just says P is M times V then. Okay. So this is already interesting. So what do we see? Momentum would be on the analog of something that's the price. Okay? So momentum gives you the quantity of the motion that's in there, how much motion is in there. And the price similarly gives you how much demand is there, how much people are asking. Okay. And that's intuitively right. Okay. So if there's no price for the goods, then they're not flowing. And if they're flowing, they must have some type of value. All right. So that's the basic idea. Okay. Now this price is a subjective thing. All right. And so is the slope of the line. The slope of the line they call the price elasticity. All right. So the agent, the particle itself, that is an agent, that's an economic agent, and he has a particular price at every particular quantity that he demands or supplies. Right, now you'll see one line goes down, the other goes up. You'll say these are negative masses. No, they are not, because you should realize these are vector quantities, and so you run this thing the other way, but then they don't run momentum the other way. They don't run the price the other way. So you should run that the other way too. So it's a vector equation. Right? Okay, that's the basic statement. So you have momentum, that is the price, and then you have how many goods you bought, that is the balance in the account. So the coordinates of your space are the accounts, and they have a balance, and this balance is increasing or decreasing, and that is the demand, the actual quantity. That's the setup, right? So you have your state space, you have some momentum definition on there, and then you make the next assumption. Okay, what is a force then? Well, according to Newton, a force has to be the rate of change of momentum. What is an EMF, an electromotive force? According to Faraday, it has to be the rate of change of the magnetic flux. Then you're stuck there. All right? So that's what a force is. So the idea is that if your price is constant, you're in equilibrium. So if you imagine this kind of Galilean relativity, you're riding in this train, and now you're going at this constant speed, you don't know what your speed is, so your momentum is constant. And a force is something that changes your momentum. Similarly in economics, a force is anything that changes your price. As soon as you start valuing things more or less, you're bidding up or you're asking it down, right? You have a force acting on you. And the idea is you should feel that without looking outside. So if you look outside, you see somebody with a higher price, sitting in an airplane, somebody has a higher price, and you get all mad. That's a fictitious force. That is a pseudo force, some kind of centrifugal force or something. The real force is what you do when you don't look at anything. All right? So we define a force, an economic force, to be the change of the price, the rate of change of the price. This is the essential part. Now, most approaches define force to be the price itself. It doesn't really work because there's a lot of reasons why it doesn't work. The real reason is that in equilibrium, all the forces the net force has to be zero, right? Now, if force is price, then all the prices have to be zero in equilibrium, and we know that's not the case. You're cool with paying something as long as the price doesn't vary. That's when you start feeling jerked around. Okay? When the prices start varying, like now, it's like walking to the bathroom in turbulence in your plane. It just doesn't feel good, Get all the stuff all over you. Okay? All right? That's the intuition. This is the intuition we take and we run with it. Once we know what a force is, I can define all kinds of other forces. I can define the spring force. I can define a damping force because I calibrate them to a standard mass, right? The standard price elasticity, and I know what it is. Now, in this way, you can do the standard time domain stuff. You have the method of analogs. You can, if you do bond graphs, you have these I, C, and R elements, right? And you can look at a spring as an amount of storage, right? So it's your balance changes. You have the balance of so much, the balance of so much. A lot of apples in storage, little apples in storage. If you have too little, you want to get more. There's a force acting on you to bid up, so you buy more apples. You know. Then you have these brokers. These are your transaction costs. So when you have a flow of goods, you got to pay somebody to transport it or to mediate the transaction. Right? That's a force, an economic force that will discount the price, right? Based on how much you're pushing through. Well, of course, if you're not selling it, pay the transaction. Okay. So what you got to see now, you can use all your kind of engineering know-how, if you have any, you know, to start building economic systems, you know. And if you're an electrical engineer, no problem. This is an inductor. This is a capacitor. And this is a resistor. You can do other things, transformers, gyrators, you name it. You can from this point on. Once you know what a force is, you're basically done. So this is the basic idea. So I wanted to establish that, and then go on with the rest of our details side of the program. So before I say what we do in practice with it, let me just say one thing quickly of the frequency domain. So this is this time domain. You can make these LTI models. You can do anything that you normally do, modeling. You can now do in the economic domain if you just follow this analog. Then you can say, well, I'm still a control engineer, and I took some classes a long time ago when we still did the frequency domain. What would that be? You know, just for curiosity's sake. And then here I wrote down the Laplace transform. You guys know all this. You remember, when you don't know this, you remember this. This is the definition of the Laplace transform. And the way I learned it, I just learned it and then did the exam and then quickly forgot about it and then just used the table. Right? Why? Because the formula made no real sense to me. So why would I do such? Now, one of the cool things of economic engineering is that everything you do makes immediate sense. You know, what is momentum? I don't know. But what is price? I know that. You know? What's a force? I don't know. But what's a price change? Well, I know that. Now, what's a Laplace transform? I'm going to tell you what that is. All right. So there's force here. There's economic force. That's so many dollars per item, you know, per year. I multiply by that factor e to the minus s. Right. Now, what is this? This is the discount factor. Right. When the t is 0, this thing is just worth whatever it is. If t gets higher, you have to discount it with a factor, you know, that is smaller than 1. And then what you do when you have a cash flow like that, you multiply it with the discount factor, you integrate out, all you get is the present value. Right? Very intuitive, right? Now, why would I use a present value? Well, of course I want to use a present value because I don't want to keep track of time. I don't want to plot this whole thing in the time domain. I don't want to say it's worth so much, you know, boom, okay? And what do? What is that S? That's just the discount rate. If I look at the real part. So what I do, I look up, and I say, what is the discount rate now? Well, maybe it's 1%, the Federal Reserve. So plug in 1% here, calculate the present value, boom, I know the value of the stock. I don't have to keep track of its whole history. All right, it's very intuitive, right? The other thing that is nice is that, of course, in engineering, we leveraged the hilt out of this Laplace transform, and we did this analytic extension to the complex plane, adding the imaginary axis. You can also think of it as a Fourier transform if you extend it with the real axis. Now, what would that be? Well, the imaginary axis, if you look at this little system we have here, that's just going to give you the fluctuation. So this is a little trader, and he's buying, and then he's got too much in storage, and he's selling again, and he's buying and selling, and he's going up and down like that, right? And then this gets damped out. You can easily see that. But what is this going up and down of this trader? Well, his inventory is going up and down because first he has to buy and then he's got to sell, he's got to buy. And when he buys, he wants to buy low but still high. So his price is going up and down too in a phase shift, of course, you know. So this we can catch on the imaginary part of that cycle. So we look at that signal, we get out the damping part, you know, we put that on the real thing. We call that the discount rate. And on the frequency part, we do the volatility, you know, how much this is volatile. So you get a present value that is quite useful. It's one complex number that tells you how much it's worth and how much frequency content in it. So you can go, if you're a high frequency trader, I remember that you were really interested in that. How much energy do I have in these or these and these locations? A high frequency, low frequency, etc. And then you can take all your time domain models, and you could do just regular Laplace analysis, frequency domain analysis, and it's very attractive. You can take a Laplace transform of these economic forces and get the value. And the Laplace transform of the demand, that's the entire quantity brought to the present. And then the transfer function becomes what we call the liquidity in markets, right? So how much the price changes if you want to demand more, right? I guess it will respond to the inverse of the impedance or something like that. The reactance, is that it? So the liquidity becomes something that you can deal with. So this whole, you can make Bode plots and Nyquist plot, anything you feel like. So we have a whole group of students that actually go and do this. A lot of master students, they take this little part of the theory, Laplace transform of this, and they go to various industry and they try to, they apply it. And this is how we write a lot of our theses. And I just want to share with you a little bit what is working for us and what's not working for us. And I guess that here are the opportunities that I see. Like one of the things you can see here is this is a model of the dynamics of a price. You can model exactly how the price is going up and down. And economic models don't do that. They see prices equilibrating quantity. So they want price stability, whatever it is, and then they will look at data and look what the new equilibrium price is, if they have one. But they don't go model a transient or anything like that. Now in industry, often they are interested in the transient because things start moving a lot. You know, there's a lot of volatility with supply lines, value change, energy prices are going up and down. So these things, this becomes more and more important. The other thing that I find is that this is chance of little data models. Most economists, if not all, have these regression analyses, you know, so all the variables are estimated, okay? This approach is different. You only need to estimate the parameters, right? The variables themselves, the prices and the position will, if you know the parameters and the initial conditions, they will just roll out of the model, right? So estimating a few parameters is going to use a lot less data than estimating all the variables. You know? The other thing that people like is that it's more predictive. So you actually build in the economic laws. You know a couple of things, you build that in, and then of course you will have noise and other things, but you got a lot of predictive behavior all in. Otherwise you have these VAR models and you always have to worry about the predictive. In Wall Street, I have to say, these people, they had always these models based on statistics, and they always worked until they didn't work anymore. So some of them were really successful until something went wrong that they hadn't anticipated, and then they all went bankrupt. Now, the only guys that were really successful were the ones who had some kind of edge, who knew something, right? My experience with statistics has been really not positive. Whereas my PhD thesis was all about statistics, stochastic control. So it was an eye-opener. I think the biggest thing that we bring is this dichotomy between what is a system and a controller. Like they will just throw everything together in one big heap and they'll try to make a model out of it. But some of it are human beings, you know, like management or government trying to do things, and other things are just things that are reacting to whatever market mechanism. And it's really difficult, and they claim this too, to do this because the human beings are hard to model, this and that, and such and so. And that's why they have a whole theory why you can't do it and why it's not a science. And one of the nice things I think of the systems and control approach is all the human beings we jam in here. All right, and then the system is just what it is. It's like you would do an autopilot. So you make a model of this airplane, and that just does what it does. And then this pilot, okay, that's on the controller, and then we can model that as a separate entity. So with most of these applications, they'll do something, and you have a system. I'll talk about one of them. And then that has to be managed by somebody. And then there's management or the decision maker. We model as if it's a controller, either an optimal controller, they have some things, or maybe some PID controller. So we have this nice separation of the two. It's a very attractive, something economists have never really considered. And so we have a couple of projects. Shall we look at these value chains, supply chains, big macroeconomic models? I'll say something about these. There's a big project we're doing right now with Rabobank in finance. So that's kind of my background. And I want to say something about that project and who's working on that. So this analog that I presented, that's just a linear analog, right? So you got this mass moving in a line and another line, and all the dimensions are the different goods, okay? And the mass inertia represents your price elasticity, and then you work from there. So that works well for commodities, like grain or money or things like that, right? But you have other goods that are called capital goods, right? So it's a little bit different. You have a piece of land, and on that land, you get some crop yield, or you got some money, and on the money, you'll get some interest, right? Or you have some population, and given your population, you'll get some labor coming out of it, right? Now, as it turns out, that should be done with what we would call a rotational analog. So the capital, that's your arm. In itself, that doesn't change. That's immutable. And the thing that's changing is the other direction where the yield on the capital is, all right? Yeah? So you need what we would say is the rotational analog. So instead of momentum as price, you use like angular momentum, and you'll get something that's we call the asset value. So it's the value of that asset because it's yielding something. I mean, what's the value of a bond? Not a piece of paper. You don't even get a piece of paper anymore, but only the interest you get on it, the coupon, right? What's the value of a stock? Huh? Not because the piece of paper or an agreement, no, because you get the dividends, you have a right to earn it. So it's always about the yield. What's the value of land? Only because you can get crop out of it. Otherwise, it's pointless. Okay, the value of a home, same thing. The bricks are worth nothing. It is the fact that it provides shelter. All right. Huh? So you see, there are these two things: that the capital direction. Huh? So this. You can have all these, this moment of inertia, it's called the duration, and then the angular velocity in percent per time is then the interest rate or the yield or the rate of return or what, they vary a little bit. All right? So this is interesting. You got a totally different analog. And then we look at how these things move. So they have these various accounts, and then you can have annuity, so you have some mortgage. And then you pay off your mortgage, so it gets less, but you also have to pay interest, so you go up, and you make something like a circular movement. All right? It's called an annuity. Huh? Everybody with a mortgage, I bet you, a lot of you suffer under this movement. You know? Huh? So this is what you have. There's also something called simple interest. You just, you know, those farms work like that, right? You have so much land, and you just get so much yield, and they just, huh? And then you have something that's interesting, it's called compound interest. So you get some interest, but then you reinvest it, and you get some interest. And then you go along to hyperbola. Right? So you see, this is you see rotations and shears, and I guess those are squeeze maps, right? These Lorentz transforms, you know, they all find their place. It's kind of pretty, you know? It's like really pretty. And then what we do, you can think of this as your assets, you can also think of this as your liability. And if you have both, you'll see you've got some mass here, some demand, and here you've got some demand for liability. So maybe your asset for a bank would be that you gave this mortgage, and a liability will somebody put their savings into a savings account, right? And you've got to balance these, right? Because this is what a lot of the bank is. People want their savings money back, but you can't renege on your mortgage contracts, right? So these moments of inertia are not the same. So what you see is that this balancing mechanism, you can model it as if you have a tire, that's in balance, and you start rotating on thing will go, start banging into the bearings here in the middle. This is important for a bank because these forces have to be, economic forces have to be absorbed by them with their reserves and other things, just like they have to be absorbed in a car when you have an axle or something like that. There's somehow the bearing forces will have to take it in balance. So you see, it's a pretty kind of thing. You can make a lot of progress. You can see the static balancing. That's just your regular general ledger, assets equals liabilities, right? And this dynamic balancing is more the value. What's the value of my assets? What's the values of my liabilities? If my assets are all worthless, then I'm bankrupt. I'm dynamically completely unstable. So this project at Rabobank, we made these economic systems. This is the PhD Koen Hutters, who's working on this. He is now on a well-deserved vacation, so he can't be here. But there he is, like any PhD students, backed with his back behind the wall, backed into a corner. Maybe some other PhD students feel the same. Can't go anywhere except make this model. So we have a whole proposal that lies there now with the kind of economic engineering model. And then the mortgagor, that's the one who takes the mortgage out, and he has his objective. He's a controller. And then the ALM department, that stands for Asset and Liability Management. So they got to manage this. This is a very important function at the bank. They are over here as another thing. These are their objectives, so they're more optimal controllers. And then this is whole thing. He is better qualified to talk about his research than I am. And several master students are working on this. One of them is here, Britt, on board, who's dealt with this little piece here. And then we have Berend, who will be working on the rotational analog and how we get a whole constellation, like a n-body problem of all these accounts in their books moving and how we keep those things balanced. Okay, that is like the first half of my talk. Okay, first two-thirds. Now what I want to do with the rest of the time, as far as I have remaining, is show you a little bit my theoretical hobby. And what I feel is really, this is really what I think. This is the most enjoyable part. So I want to share. All right, that's enough. So one of the problems you have with this method of analog approach to that is that I guess that's a problem all engineers have, is that somebody comes around and says, well, why is this correct? I mean, can't I do something completely different and also get good results? I mean, how do you know, right? This is the right thing to do. So first I would give these answers like, well, I don't care, as long as it works. And that's a little bit, right? So what I want to do with this type of analysis is two things, really. First, so you see that this approach is the only approach. There's nothing else. A little bit like how Lagrangian and Hamiltonian mechanics explained why Newton was right. And you can't do anything else. You can't define force. It just doesn't work. Right? And the other is that sometimes these analog models are quite limited. We saw this already, that you can only use the regular one for commodities. You have to invent this rotational thing for analog for capital, but then you have weird rotations. These kind of approaches give you something more, general, where you can just do these type of analysis. All right? So, and it's just really attractive. I mean, so I want to first go through the Lagrangian approach, then the Hamiltonian. then a little bit of thermo, that doesn't look like a little bit, and then get to symplectic geometry, which is really my, my current kind of. So you probably know this, but the way you would do a Lagrangian approach to all of this is you define something called the action, which is integral of a Lagrangian, and you minimize that. And when you do that, you figure out that you get the Euler-Lagrange equations, and then in specifications, you get Newton's law or whatever. That's the approach. And this is the approach everybody takes. Also, when Newton's laws don't work, that's what Feynman took with the path integral, etc. Now, how would that work out in economic engineering? Actually, it becomes almost trivial. Because a particle, why does it minimize its action? This is just a little bit weird. Why would it do that? Right? But an economic agent, why wouldn't it want to maximize its utility or minimize its cost? That's the first thing you want to do. You don't know yet what cost is, but the fact that you're optimizing something, that is clear, right? That's what you feel. Very attractive. And in economics, that's also considered, the thing to do, right? So what you do is you look at the action as the period cost, and then the Lagrangian just becomes the running cost, all right? And then you integrate that Lagrangian out over the period, your lifetime or your planning horizon or your whatever it is, your expiration date of your option, I don't care, all right? So here what can you minimize? Well, it has to be something that's valued, say, in dollars or euros. So you're stuck. That's got to be in dollars. All right. So your Lagrangian has to be in dollars per year because you got to integrate that out over time. All right. So you immediately know that the analog to energy has to be sort of an income. All right. But you can do a little bit more. You can look at the kinetic co-energy. And if you look at our regular supply graph, you can actually look at it as the area underneath this thing. And these economists that call the cost or the expenses associated with it. Right? It's pretty clear because you look at an extension of your demand, so your demand a little bit more, you multiply that by the price, then that's just a marginal cost. So if you calculate this marginal cost, you get the total cost. Right? Now, then you have, these are called sometimes the direct cost, but the cost associated with selling. That's the kinetic co-energy. Then the potential energy, if you figure that out, but remember this was a storage, now a spring. So these are the benefits of ownership as you figure it out. Now the benefits, you can't add them to the cost, you have to subtract them to get a cost. So your total cost will be exactly this expression. Minus sign taking care of everything that always seems so mysterious, just taken care of. Can't be simpler. All right. Then what's the canonical momentum? Well, you just differentiate your Lagrangian with respect to your velocity. Well, here you differentiate your cost with respect to your demand. Well, you're going to get something in dollars per unit. Of course, that's going to be the price. I mean, that's the per unit amount of money you're willing to pay for this. All right. So the momentum is, of course, the price, and these are the units. I mean, you're stuck. Right? And you solve the Euler-Lagrange equation, you're going to get that the force has to be the equilibrium has to be the change in price. So you're stuck. All right? You're stuck. Mass is the price and elasticity. They look at the inverse of the mass and they call that the price. So there's two things. First, you're stuck. This has to be it. And secondly, it kind of makes everything easy. This is actually easier than remembering all these analogs. I mean, you can just write this down. All right. Similarly, for your Hamiltonian approach. So normally, what you do this genre transform that comes out of thin air somewhere. It's just what you do, right? And then you figure out it's equal to the sum of the kinetic and the potential energy. So your minus sign becomes a plus sign. Your T star becomes a C. Now, and you get the energy. All right. But look at this Legendre transform. This is the price, that's the quantity demanded. So if you're a supplier, that's your revenue. All right, you subtract your cost. What do you do when you have revenue minus cost? Well, you get your profit. It's usually called the surplus. Okay? So the Hamiltonian is the surplus. And you can even see it's the sum of the direct surplus. That's the surplus you get by selling at a price higher than you would want to have. plus what you have in storage, which is a sort of potential surplus, which you couldn't be selling. All right? That's the potential energy. This can't be easier, actually. You know? You can write down Hamilton's equation. Here is some deep result in economics that's called the Hotellics lemma. They prove it. And there's something about economics that I don't like. It's not that the proof is wrong, but the way they approach this business is they want to prove something, so they make a bunch of assumptions, which I don't know where they came from. And then under those assumptions, they'll prove this other thing that you also don't know where it came from. You know? And I guess that's just a function of having a lot of mathematicians move into your otherwise economic geared profession. But what I like about this is you start from a basic point. Okay, you minimize action or maximizing utility. Now, what steps do I need to take to get here? Instead of saying, okay, under these assumptions, I can prove that, right? All right, so you get this, and this is then what they sometimes call the law of scarcity, right? This is just the spring law, the potential law. Right? So when it gets scarce, you know, huh? All right. Now, this is also kind of, thermodynamics has also been a pet project. This looks a little busy, but it really isn't. Not that much going on. You see, economists have also used a lot of thermodynamics. And the way they approach it is a little bit like how Clausius in the 19th century approached thermodynamics too. They just assume there's something called entropy that has a fancy word that you don't really know what it is. You describe it with some bad names like amount of degree of disorder or something. Nobody knows what it is. And then you just assume that it's there or by the second law, and then you just work with it, and then you get used to it. You know, and then if you're used to it, you call yourself a thermodynamist, and you go to PhD. Right? So, but everybody else finds it hard. All right. Now, what then happened was people like Gibbs and I guess Boltzmann, they said, well, this is weird. We have all these particles flying around. You know how they behave. You know, then why wouldn't we know how a gas behaves and calculate its entropy, right? So they kind of did this, and this area was known as statistical mechanics. Now, one thing we can do now with our engineering analogs for Newton's law is just copy this process. And then we know what entropy is, right? Huh? So I know what a particle is. That's just an economic agent. I know what a direction is. You know, that's just a different type of good. I know what a velocity is because that's just the quantity demanded. I know what kinetic energy is. I know everything. So I just start copying. So if you do that, you kind of get this. You see, you get that the entropy is the degree of diversification. Diversification is when your income gets distributed in various goods, you know, so you're very diverse, you know, different types of stocks or different types of things, you know. And distribution is when you distribute fairly over different players, market players, people, all right? Huh? And this is exactly what happens in mechanics, right? So this is not very diverse, only one good and one guy is doing everything, huh? And here everybody's going every which way, demanding this, that, and the other, and you get the situation of an ideal gas. All right, so the income is better distributed, but and the portfolios are more diverse. Right, and then we say that is increase in entropy. Now the temperature comes down, there's incentive to do that, right? Okay. The dimensions are the different goods, there's the particle, and you get all these different chemical potentials. And this is an incentive for agents to come or leave the system, maybe immigration, right? So incentive for immigration. But this is an incentive for innovation to create various types of goods so that the surplus can go seep in all this. You know? So you got a nice space to do this. You can draw these kind of Gibbs frontiers, they're called periodo frontiers, et cetera, et cetera. Then you can do statistical mechanics, so you count the number of microstates. Those are the price quantity combinations. Those are all the options you really have as a society to distribute everything. Who pays value to what good, right? Yeah. You take the log out of that. Why would you do that? Well, if you want to make profits, you got to choose. You got to find the agent who does that, and if you do that, and if you do that, you will take the log because you can define it to, you know. Yeah? So the number of choices goes with the log, right? Like the amount of bits goes with the choices you can make. So you just take the log, you get the number of choices, huh? Then you can calculate the partition function. It becomes the opportunity function. Take the log out of that, you get the free energy, the Helmholtz free energy. It just becomes the free surplus. So if you have two big economies and you want to trade with them, it's a Carnot machine. You know exactly how much you can pull out of it, etc. Right? So it's just like everything becomes easy, right? I have 1 more minute left, so I'll wrap up. And recently, what we've done is we've tried to put this all together. See, one of the problems with the Lagrangian and the Hamiltonian analysis is it doesn't apply to damping. Okay, it just doesn't. You know, you can add a Rayleigh dissipation function, but it doesn't. Now, this is a big problem in economics because a lot of it is damping. Consumption is damping, depreciation is damping, transaction costs are damping. You know, so you can't leave it out. So a lot of our efforts theoretically have been to include the effects of damping in the Lagrangian and Hamiltonian effect, not just Newtonian. And this is where I find really a very nice thing. We're using something called symplectic geometry. You have this fancy things like a Liouville form, a symplectic form. But the nice thing is it's like that's immediately a value. The symplectic form just becomes a unit of value. You multiply a small price change by a small quantity change, you get something in dollars. It's just a unit of value. And if you limit that, it becomes like the Planck constant. You say it can't be smaller than that. You know, it's like a cent or 5 cents in Holland, I think. You can't get smaller. So if you buy something, you will never know whether that thing was 5 cents and you got one good, or the thing was really 2.5 cents and you got two goods if you look at the transaction. So you see that this all goes really nicely parallel. You can calculate the Hamiltonian flow, and you get the circulation of money, right? The circulation of value. It goes spins around. And then what we do, and this is all new, done with Koen and Emil and me, myself, we define this contact form, and it tells you how this thing gets damped. So you go with an extra dimension. I'm going really quick here, but this is the stuff I love to talk about. You get a different Hamiltonian flow that has both the circulation of the body and the sinking, and a sinking factor that goes away, right? Like depreciation, the money just gets dissipated. All right. So it's a very pretty picture. And it allows us to do these kind of things, allows us to fuse from an engineering perspective, a fused port Hamiltonian system, like from the stuff that others have worked with the port Hamiltonian, but it doesn't include damping very well. They add it on. And they also have thermodynamic systems that they go to a contact bundle and they do it there, but they haven't put them together. This allows you to put the two together, you know? So you have really thermodynamics and mechanics together, you know. So not only are you putting entropy back into controls, but also entropy, right? Like diversification. So you could control for it potentially because you have it as an extra variable, because you add it as an extra variable, right? The dissipated energy of P, Q, and then it's used. You can make a total expense Lagrangian. So you take your direct cost and you add to it the potential cost and then also the expenses and other stuff that gets expensed out. And another little project of mine is to use the split patterning algebra because it's isomorphic to the general linear group, GL2R, I believe. And that's a group of A matrices that does all these systems. And you can, I think I exceeded my time a little bit. So rather than go on, I think maybe.
There will be a time for questions.
Just a comment. I think Arjen van der Schap.
You think you what?
Arjen van der Schap put for dynamics together and to tell you system magazine is very my favorite.
Oh, I'm very interested in this. I know that, yeah, but what they do is they have this J matrix that has the symplectic structure, right? They call it the structure matrix. So the symplectic structure is in here, right? And then they add this positive definite matrix. And then I believe they look at the gradient, and this is how they calculate the flow, right? The Hamiltonian flow, right? The Hamiltonian flow, I don't know how they write it, but it's just the Hamiltonian flow. This is the velocity. The problem is this is not symplectic, right? So you cannot use Hamiltonian and Hamilton's equation because this is a positive definite matrix. You know, this matrix is okay because I never know when the minus sign is there, right? So it has no trace, right? And it's a Hermitian. But this one is not. This one is positive definite. So that's the problem. So the approach here makes one new J matrix in 3 dimensions. So you get, and then there's a gamma here, and then, you know, but it remains, you know, it remains skew symmetric. That's the big difference. That's the big difference. So they have a Riemannian metric they add on it. That fouls it up. You're right. So you need a contact form, right? Now, usually what they do is they'll use something like, well, let me just don't say what they do. Let me say what I do. So what you do is you look at the change in the internal energy, right? And that's going to be if you subtract the friction force, okay? And that should pull back to 0 on the solution manifold, right? But this friction force is gamma times the canonical momentum, right? Well, gamma is B divided by M. Why? Because B divided by M times MP is M times V is just B times V, which is exactly the friction force. So here you see the trick. So this here, this is the tautological one form. This is the real form. So if I pull this gamma out, I get gamma times some new thing, say Q0 minus P dQ. So here is my new dimension, you see, but I maintain the tautological one form, and I can take, if I take the exterior derivative, I just get this minus dP dQ, you see, and I get back my symplectic structure. That's the trick. Well, others will use a one form here, but it's not phrased in terms of the symplectic structure. It's separate from the symplectic structure. This one, you see, is defined in terms of the symplectic structure. That allows you to do it all. So if you have a symplectic structure, see, this is a contact structure. If you can symplectify, you're in 4 dimensions. Then you can just write down Hamilton's equation. Then you project down again because you have your tangent space, your cotangent space is a projective space. You can project down again, and then you write the contact. So you get a symplectic form that looks like this, plus, and then there's a new, like a new one. And this one is then keeps track of how much of the symplectic mass is the amount of value is actually escaping out, right? Okay. And then you go to a new state space where you have P, Q, and U. And U is the dissipated energy. Because I project from this one down, right? You see, that's the way it works. Right? And they don't do that. They have separate. They have it separate, and they add a Riemannian structure, and this fouls it up. That's why you can't do Hamiltonian mechanics. It's like a Rayleigh dissipation function in Lagrangian. You can just add it, but you won't have, you know, the structure of the tangent bundle. You know, this thing is just for a Lagrange optimizer. You can do that too, but what do you have, right? Yeah.
Yes, I mean, just out of curiosity, like, because for example, you mentioned that in this part of entropy, you have more choices, I guess, in the market, you can compute entropy. I was just like curious, like, could you do something like, oh, I don't know, the entropy, economical entropy of the Netherlands or something like that? Have you done that?
No, because have you calculated the entropy, the real entropy of the Netherlands? You know,
Well, I mean, that's.
You have to define, but it's better to do it in a macro thing, right? Huh? So what would you do if you define entropy? I mean, you will look at the change in, the heat, and you divide by the temperature, I believe, right? Huh? Now the temperature, that's this incentive, and you will find from the kinetic theory, this is the average surplus, okay? So it's average kinetic energy. So this is where it's start getting useful, all right? Huh? This thing here is the amount of welfare. So that's the amount, comes from this U here, right? This is how much of the surplus you've dissipated, right? This is dissipated energy. It's just how much transferring of that to somewhere else. If you do this, then you could calculate the entropy, right? And then you just get a number, which is the diversification, but you can kind of see what's coming from, because it will just give you a measure of the pluriformity of your society. How diverse is it really? Now, how many different goods are there, and how many people are in there enjoying all these goods and trading them? That's what it measures. So if you do an information theoretic approach, that's what I would do, for instance. I would calculate the Shannon information of this thing and put a minus sign in front, right? Okay. So there's just different approaches depending on whether you want to have a welfarometer, which is a thermometer, right? So you have to keep track of this thing, and then you have to be able to measure those, or you have to do it in an information theoretic approach, something like that. My answer is more the theory. You see, if you don't have this theory, you're just guessing. You can get far, but this just gives you, okay, what's the definition? What is it? Well, okay, then I'll just do that. Huh?
Maybe you also or was it you did this?
Yeah, I was raising my hand. Yeah, just a quick question. Sorry. Regarding slide, I think it was slide 9, when we were talking about statistical mechanics. I think that's one of the, I guess that one of the assumptions of statistical mechanics is that you need to have independence between the particles. But would that hold like in an economic sense, where the agents actually sort of influence each other, or like the economic agents themselves can influence the system where the part of?
Yeah, that's a good question. I think it's not the case that it's an assumption. I think it's more that if you have a microcanonical ensemble, then this would be the thing, right? But you may have something else. So it's more of a procedure for defining it rather than a limitation of its applicability. Huh? So I think the way they do it, entropy is just defined for whatever system, even if it's not an equilibrium. Huh? And there's no real limitation on what is, of course, you have quantum issues and things like that, right? So it's not like it's practically limiting you, the setup, I think. The problems that are practically limiting you is just a little framework, and you still have to make all your assumptions. And some of them, you can take an ideal gas, and I have a student who worked out for an ideal gas, but what sucks about an ideal gas is they don't interact, right? They're all buzzing around. So how realistic is that? So then you have to get off on the Bowles house or gas or something like that. And so you go crazy very quickly, right? So I think that's more the limitation, not on the theoretical assumption side, but on a practical side. Well, how do I do this? Like this other question, well, I can generate some ideas, but where do you get your welfarometer from? Like I know what a thermometer is. What's this welfarometer? Right? You got to build it. Huh? So there's a lot of stuff to do. But my message is always, at least you know what you're doing, right? And before you're just guessing, and then you never know in the end whether you guess right. Maybe before they had the definition of temperature as the partial derivative of the energy, they were also just guessing, like Celsius and Fahrenheit. One guy put it in his neck and the other puts it in water, They don't really know, I think that's more the approach to take,
maybe in the interest of time, we can stop here, but if you have additional questions for Max, I think he will be readily available to answer them.
This is all I talk
So let's
about
thank
anyway.
Max again.